Vinylic and Aryl halides cannot undergo SN2 substitution. So we just finished a series of reactions where we were reacting at the allylic carbon. The allylic carbon is an sp3 carbon next to an sp2 hybridized carbon, which is in a pi bond. But if the alkyl halide has the halide bonded to the sp2 carbon that is in a pi bond, nucleophilic substitution is not possible because of repulsion of the pi electron cloud. Electrons of the electron cloud and electrons of the nucleophile will repel each other, preventing nucleophilic substitution. So, further showing you that why this will not occur, the sp2 carbon does not make a stable carbocation, does not. So E1 and SN1 are not possible, and SN2 is not possible because of the pi electron repulsion. So those reactions, the reactions that we are working on in this chapter, will not occur at sp2 carbons that have halogen bonds. A vinylic halide can undergo an elimination reaction, and it is only able to go through an elimination reaction because it will produce a triple bond, which is a stable bond type. But there must be a very strong base, stronger than hydroxide. In fact, the pKa of the conjugate acid of the base should be 35 or higher. For the base, for its conjugate base to be sufficiently basic to remove the proton of the carbon, the beta carbon. And the beta carbon, which will be selectively removed in this E2 elimination product, is the hydrogen of the other vinyl carbon. So the vinyl hydrogen and not sp3 hydrogen, the sp3 carbon hydrogen. So not this one. Okay, solvation. Reminding you, polar solvents stabilize charges. Solvation. Ion-dipole interactions between a negatively charged species and water, showing solvation of the negative species, and showing solvation of the positive species on the right with the negative oxygens orienting around the cation. And polar solvents stabilize these charges, and solvation is, if solvation is occurring, those conditions favor SN1E1. If a reactant is charged, increasing the polarity of the solvent will decrease the rate. If the reactant is charged, increasing polarity of the solvent decreases the rate. Yes, okay. So My pen just fell apart. Just a moment. What happened? Where'd it go? Pause. Okay, now that I've found the piece of my stylus that fell off, let's get a laser pen. Okay, so we have reactants are more highly charged in a more polar solvent. The rate of the rate is lowered and it occurs more quickly, lowering the activation energy, having a more polar solvent. When the reactants are more highly charged and they're in a less polar solvent, this graph is not clear. If they're comparing reactants, they should have the same energy. So this should be down here. Just let me refer to the book really quickly, because I think they're drawing incorrect. Okay, so for this graph, they incorrectly drew the two peaks. What you need to know is that the reactants are at the same energy point. So these are of equal energy, and the graphs should be more overlapping. So technically the blue graph should have its baseline down here, okay? Which means that the red graph has a taller transition state comparing this blue line to the red line. Here, how about a highlighter? Yep, comparing the red line highlighted in yellow to the blue line highlighted in blue. Okay. Knowing that the base, when they are at the same energy level as they should be, the red would be taller and therefore have a higher activation energy. And so the reactants, when the reactants are more highly charged and in a more polar solvent, the activation energy is greater than in a less polar solvent. And the reason is that the charge of the reactants is stabilized more by the polar solvent than the charge at the transition state. And when the reactants are stabilized by the polar solvent and solvated, then the nucleophile has less access to form a bond to the reactant. If the reactants are neutral, and then increasing the polarity of the solvent will increase the rate. So again, these lines should actually be starting at the same point. And if they do, then that would mean that the blue peak is slightly taller than the red peak. The blue peak is slightly taller than the red peak. So that the red has a lower activation energy for a neutral reactant, which means it will occur faster. Whereas when we have a charged reactant, The blue has a lower activation energy. So having a less polar solvent will have a lower activation energy for a charged reactant, and the reaction will occur more quickly. So how solvent affects the SN1 and the E1 reactions of the alkyl halide. In the rate determining step, the transition state, it has a greater charge than the charge on the reactants. Okay? So if the reactants are neutral and the charge on the reactants is less than the charge on the transition state, increasing the polarity of the solvent should stabilize the transition state and the reaction will occur more quickly. So for SN1 and E1 reactions, because they go through a carbocation, having a polar solvent is favored and makes the reaction go more quickly because it stabilized the positive charge at the transition state. Transition state, double cross, and rate is faster. So polar solvents are good to use for SN1 and E1 reactions. The rate of the SN1 reaction of an alkyl halide increasing as the polarity of the solvent increases. So water is a very polar solvent, more polar than ethanol, which is another solvent that we can use that is polar. Where's my mouse? This is a little tiny dot because I had the pen on. Okay. So at 100% water, which is more polar than this 100% ethanol, the relative rate of reaction is 1200 to 1. That means that for every one reverse reaction where we make the reactant, we make 1200 molecules of product, right? When we decrease the polarity, 80% water, 20% ethanol, 50% water, 50% ethanol, 20, etc., until we get to ethanol, the relative rate of reaction decreases as the polarity decreases. Okay? So SN1 reactions occur more quickly in polar solvents. That's the takeaway. And then how the solvent affects the SN2 and E2 reactions of alkyl halides. In the SN2 and E2 reactions, the nucleophiles are usually formally charged negative. So if one of the reactants is charged, then and the charge on the reactants is more than the charge at the transition state. Okay? Because at the transition state, we're forming a new bond and the charge is lower because there's a weaker base forming and there's not actually a formal negative charge at the transition state where there is a formal negative charge in the reactant. So now the reactants in SN2 and E2 are more charged than the transition state, which means that a less polar solvent that doesn't interfere with the nucleophile and solvate the nucleophile is favored. So increasing the solvent polarity will stabilize the reactants, which means that it will take longer for the reaction to occur. So the reaction will take longer because a polar solvent stabilizes this hydroxide ion and so that it doesn't care about the positive carbon. It's got positive solvent. Why does it need to bond to the carbon that's positive if it's surrounded by positive solvent. Okay, so that's why the polar solvent would make this reaction, SN2 and E2, slower. So what solvents should we use for our different types of reactions? For SN2 and E2 reactions, we should use a slightly polar but aprotic solvent. Okay, so polar aprotic solvents are less polar than polar protic solvents. Okay, so on our graphs, they were referring to more polar solvent and less polar solvent. You should think of a more polar solvent as something with a OH or NH bond. These are more polar. And less polar would be something like dimethyl sulfoxide, which we mentioned earlier, which doesn't have a heteroatom to hydrogen bond. Okay. So still polar, but just less polar because there's no OH or NH bond. Try to get the highlighter back, or the laser pointer, okay. For an SN2 and E2 reaction of an alkyl halide with a neutral nucleophile or base, so an uncharged nucleophile or base, such as an example of a good base for SN2 or E2 that is uncharged NH3. These should be carried out in a polar solvent. Now, not necessarily a protic solvent, but simply a polar solvent. So a more polar protic solvent, or more polar protic solvent, or just in general a polar solvent. For an SN1 or E1 reaction of an alkyl halide, they should be carried out in polar protic solvents. Protic polar solvents like water and alcohol. Okay? Good. Williamson ether synthesis. This is a specific type of reaction, and you may even have somebody ask you, what would be, this product is made by the Williamson ether synthesis, what are the reactants? I've seen questions like that on the ACS exam. And so they give you an ether and they say it's made by the Williamson ether synthesis. What were the reactants? And then you have to know that the Williamson ether synthesis is the reaction of an alkyl halide with an alkoxide ion. Okay? So this Williamson ether synthesis is the reaction of an alkyl halide with an alkoxide ion, such as methanol or methoxide or ethoxide. These are examples of alkoxide ions, basically a deprotonated alcohol. So we take an alkyl halide and we react it with an alkoxide ion, and that will give us an ether. How do we make alkoxide ions? We treat an alcohol with sodium hydride. Sodium hydride, which is basically Na+. What is this doing here? I don't know. anyways, nope, still there. Okay. Sodium hydride, which is sodium cation plus hydride anion. And this sodium will be a spectator and not unchanged, but the hydride will abstract a proton from the alcohol to make H2 gas. So here are a few examples of the Williamson ether synthesis. Propyl bromide reacting with butoxide ion to create butyl propyl ether. And the butoxide ion was then made from butyl alcohol using sodium hydride to remove the proton. So we would have hydride ion, and sodium cation is somewhere off in solution. The hydride ion bonds to the proton, negative, the electrons go to the oxygen, and that gives us our butoxide, 1, 2, 3, 4, oxygen negative. And then our butoxide will go and bond, whoops, let's change colors. Butoxide bonds to the partially positive carbon of the primary alkyl halide. The bromide gets kicked off, and that gives us our butyl propyl ether. Or if you recall, the IUPAC name should be longest chain is the butane, and then the shorter chain bonded to oxygen is the prefix that represents the carbon number, prop, followed by oxy to represent the oxygen atom. And then we say that in the butyl chain, the longer carbon chain, the first carbon bonded to oxygen is carbon 1. So this would be 1-propoxy butane. And there shouldn't be a space between the propoxy and the butane, even though I accidentally have one. So. But I can fix that. I can totally fix that. Draw, select, scoot it over and down. Okay. There. See, I can fix it. Now there's no space. And then they had a second example of butyl bromide instead of propyl bromide. And if it reacts with a propoxide ion, you would get the same product. Okay. The Williamson ether synthesis is selectively an SN2 synthesis. It will not occur if there is a bulky base. Remember, if we have a bulky base, that's going to favor the elimination product. So we would expect the tert-butyl ether, but we would primarily get the eliminated alkene from the ethyl bromide. And this ether would form from a it would not form. So no ether is formed according to our notes. But if we have the less hindered group, should be the alkyl halide, so the alkene here is the major product, and we have a minor amount of substitution product. If the alkyl halide is tertiary, the Williamson ether synthesis does not occur, and we only get the alkene. So for the Williamson ether synthesis, it is favored when the base is not, when the basic oxygen is bonded to a primary carbon, and when the alkyl halide's halogen is bonded to a primary carbon. So both alkyl halide and alkoxide should be primary in substitution. Using elimination reactions to synthesize alkene will be our next topic. We are so close to the end of this chapter.